Hello, this video is going to look specifically at just the energy bar charts. Right, and we're actually just going to look at the energy bar charts for just a closed system. So we're going to look at a couple of examples. We've used this worksheet for a few things. I've already done a video called pie charts and bar charts, what's the diff, right? So it's like, what's the difference between the two of them? And I did the first example off of this for that. I think maybe I'll work through a couple of more just with a closed system. And then I'm going to change to just some other examples that I have and look at those. There will be also a separate video that is looking at these bar charts for just an open system. So, and I will look at the same examples for those, probably making the system open instead of closed. So to jump in and get started, I've already looked at this first one. This one with the double arrow by is the one I did in the what the diff video, or what's the diff video. So we'll look at probably maybe just 2 and 3 off of this, right, to look at these energy bar charts for a closed system. I will also do these 2 and 3 for the open system from this part C, and then we'll switch to another worksheet and look at both open and closed for a couple of them that deal with springs, because none of these have really dealt with springs yet that I've worked at in any of the videos, and I want to make a couple of points with that some folks had some issues with the first time through. So let's jump in and go. Let's take a look at number 2. A ball rolls down a hill and stops. Once again, if we want this to be a closed system, this is a closed system only video. We need the ball, the earth, and I'm just going to write it the surface, right? The surface of the hill. Once again, with these LOL or energy bar charts, these circles are to write the system. So at a glance, by looking at this, I should be able to tell if the system is opened or closed by knowing what the interaction is. Because you will either have listed all of the objects that have all of the energy storage types within the interaction, and I know the system is closed, or there'll be an object that is missing that there's some energy involved, which will make and that object would be out here in the surroundings. Once again, inside is the system, out around is the surroundings, and if the object is out in the surroundings, then the system would have to be open. Once again, we're going to need to list all of the different types of energy storage within the interaction. If a ball is going to roll down a hill and stop, we are going to have gravitationally stored energy, we're going to have kinetically stored energy, and thermally stored energy. You can just make up an energy storage type if you want for the last part of this diagram, or we can just ignore it. I'm choosing just to ignore it and just writing out the gravitationally stored energy, kinetically stored energy, and thermally stored energy. Once again, please, if you would, draw all of these in the same order going across here. That way it makes it easier to see what's going on with your model. So if a ball rolls down a hill and stops, what we're going to do is once again, above the diagrams, we're going to list kind of the portion of the interaction. This is going to be at the top, stopped. All right, once again, kind of diagram it out at least enough that, I'm going to move my comma over a little bit so that I can determine what's going on. So here it is at the top of the hill, it is stopped. Here we're going to say it's about halfway down the hill. And here it's going to be at the bottom, and it says it is stopped also. So this is at the bottom, stopped. Now, by definition, there's a few things that happen with this problem. If something is as high as it possibly can get, all of the energy is going to be gravitational. If it is moving, it will still have kinetic energy also. There are some of you that somehow seem to think, from what I've looked at your work, that you think it can have either one of these energies but not the other. It can have both. There's gravitationally stored energy anytime an object can still fall further. There's kinetic energy anytime an object is moving. At the top, however, in this case, it is stopped. So we need a number of bars of energy to start with. Once again, I don't know that it really matters how many. I'm going to choose there to be 6. Once again, since it's more than 4 or so, it might be a little difficult to kind of at a glance see how many is there. It's very helpful if you write a number off to the side. So here there are 6 at the top, and that is it. It is stopped, so there's no kinetically stored energy, and there really is nothing yet that has done anything to make any of this thermally stored energy. Halfway down, right? Halfway down, it now does have kinetic energy. And if it is halfway down, right, there will be less gravitationally stored energy. And just kind of looking ahead, if this ball is going to stop at the bottom, actually, let me just work to the bottom, or the end of this first. All of the energy is now going to be thermally stored. So there's 6. So there is no gravitationally stored energy left. We are assuming in all of these diagrams and things, anytime there's ramps, at the bottom, the gravitationally stored energy is now 0. Since it has stopped, there's also no kinetically stored energy. So that means the only energy storage type that could be left would be thermally stored. So the question is halfway down. Well, what I've seen a lot of you do halfway down is if we're starting with 6 bars of energy and you're saying, okay, halfway down it should have half the gravitationally stored energy left, and that's true, right? And there should also be some kinetically stored energy because it's moving, and you just ignore the thermally stored energy altogether. Well, if it's all going to turn to thermally stored by the end, halfway down there at least needs to be some, right? And I don't know then if it makes sense to say that if this is 3 and this is 2 and this is 1, or somehow they need to add up to 6. Maybe 6 was not the best number for me to start with. I maybe should have started with something that makes more sense. And I don't know if this is even halfway, because technically halfway down there should be 3 instead of the 6. But at least somehow we need to proportion out this energy, so there is some thermally stored energy, there is some kinetically stored energy, and there is some gravitationally stored energy. All right, so there we go, something like this. And once again, I don't really particularly care about the exact bars of energy, but what should definitely happen with this problem is that the gravitationally stored energy should be getting less as the ball travels down the ramp or the hill. The kinetically stored energy should be getting bigger, and the thermally stored energy should be getting larger also as it rolls down the hill, since this one is going to stop. Since it does stop, it means there does have to be some, at least, friction involved, and friction will take these energy storage types and transform them into thermal energy. So I don't know, at least some sort of breakdown like this would make sense. The most important thing is that the total bars of energy remain the same, because this is a closed system. Once again, we'll look at an open system one in just a moment. All right, now actually I want to change my mind. I said looking at number 2. Let's actually look at number 4, where a ball is dropped and it bounces until it stops. So it's kind of similar to number 1, but we've got a few different things going on. Once again, we need the earth and the ball for the gravitationally stored energy at the beginning. Oh, I'm sorry, I need to move this up. And maybe I can move this down. Still can't. Yeah, there we go. Ball is dropped and it bounces until it stops. And then we also need the floor. We'll assume it's the floor, not the ground, that is causing this thing to bounce. Earth, ball, floor. And actually, I want to take this through a couple of interactions. A couple meaning 5. Because this is one that several people miss. So I'm going to actually get rid of this bar chart, because these should always go bar chart, system, bar chart, system, bar chart, system, bar chart, system, bar chart, right? There should always be a system between these different bar charts just to kind of track what's going on. So just in terms of order, this is 1, 2, 3, 4, 5. So I do want to look at 5 different positions with this interaction. So this one is held at top. Held meaning not moving. This is right. Actually, change my mind as what it is. We're going to do right as ball hits. Then let's take a look at, I'm trying to actually look at some different things, and I remember where most of you made most of your mistakes with this. We're going to look right at bouncing. I'm not sure if that's the right way of diagram. I'll get back to that in a minute. I'll let you know what I'm thinking of. So this is after first bounce at top. And let's just go all the way to after third bounce at top. So this thing's going to bounce at least 3 different times. It might bounce 5 times, 6 times, whatever, but it's going to bounce at least 3 times. And we could keep going with this, right? We could do after the 4th bounce, after the 5th bounce, after the 6th bounce, and eventually at the end we could say after the ball has stopped and hit the floor, and at that part it would be completely thermally stored energy. So I could have put that on here too. But let's just do this, right? So once again, I'm just going to label out this first one, and then in the interest of time. So the first one all the way across here is going to be gravitationally stored energy. The second one is going to be kinetically stored energy. The third one is going to be elastically stored energy, and the last one's going to be thermally stored energy. And by the way, I'm going to start doing something different with thermally stored energy. I should have done that with the last one. With thermally stored energy, since we did that with pie charts, I think we're also going to just darken out these bar charts also. So it makes it easier to see at a glance which type of energy, which of these energies are thermally stored. All right, so held at the top. Again, I'm just going to choose, we'll try 6 again. We'll see how this works. If I was a completely awesome physics teacher, I'd work these all out ahead of time and make sure they work out. But I'm just kind of doing these as we go. So we're going to say that there's 6 bars of gravitationally stored energy at the top as we're holding this. There is no kinetically stored energy. It's not moving. The ball is not being deformed, so there's no elastic. And really nothing else has happened to cause any thermally stored energy to be involved. Okay, so right at the ball, as the ball hits, we're going to say something as something hits. That means it's going the fastest it possibly can, which means at that point, 6 of them are kinetically stored energy. So at the top, it was all gravitationally stored. Just right as it's ready to hit the floor, it has all been now transformed into kinetically stored energy, which is our second one of these. So once again, there was gravitationally stored, kinetically stored, elastically stored, and thermally stored. Now, so as it's bouncing, right, the reason things bounce is because the kinetically stored energy is turning into elastically stored energy. Right? So when this thing bounces and it squishes and it bounces, it squishes, and let me put it this way, right as bouncing and stopped. So as it keeps bouncing and kind of squishing down, right as it stopped at the very bottom, now it is all elastically stored. However, elastically stored energy, when objects are deforming and bending and doing like that, part of that is always now going to be stored thermally. And I don't know if it's going to be a 4:2 ratio, but at least some of that is going to happen. Right? So we do have the elastically stored energy that came from this kinetic energy that the ball had when it hits. But now we also have some some thermally stored energy. And once again, once we have thermally stored energy, that's going to stay thermally stored energy. So when it goes back up to the top after that first bounce, there you go. Thermally stored energy. Which means at the top, oops, sorry, wrong place. We don't get all of the initial gravitationally stored energy we had. We started with 6 bars, now we only have 4 left. And then now it's going to depend upon how it bounces and what's going on and percentages and all that. But after the third bounce, right, at the top, now it might be 4 bars that are now thermally stored, and we might only have 2 bars that are gravitationally stored. And as this ball continues to bounce, more of this energy storage becomes thermal, right, because of what's going on when this thing hits and what's going on elastically. Because anytime things are bent or stretched with elastic energy, there's also always some thermally stored energy that goes along with the elastically stored energy. Right? As this thermally stored portion gets bigger and bigger, the part that convert back and forth and change back and forth between the kinetically stored, gravitationally stored, elastically stored is going to get smaller and smaller, and eventually the ball will be completely storing all of its energy thermally, and it will stop moving and sit on the floor. So this is going to look something like this. And there you go. So let me just do one more example off of a worksheet. And just so that I can work on this one both ways, I want to change this diagram just slightly. I'm going to zoom out a little bit. Can't quite get that where I want it. So we're going to say it's the system, the ball, the table, plus the spring to start with. So let me actually just get rid of that, not the spring, and say plus the spring. So it's going to be the spring also. But I'm going to leave this here because I want to do the same. Actually, no, let me just get rid of this. I'll print a new copy. Because I want to take a look at this same example when I do the open system one. But if it's a closed system, it has the ball, the table, and the spring, all of it all together. So this is ball, table, spring. Oh, and I grabbed the wrong one of these. Give me just a moment. Oh. Okay, no, this is fine. Ball, table, spring. And ball, table, spring. So this one, rather than give it to you words, I actually gave you some pictures to go with it. So here's the ball is moving at the start. Here it just hits the spring, and here the spring is pushed all of the way in. So this says a ball slows down across the level table, hits a spring, and slows to a stop. So it is slowing down the entire time, right? It hits the spring, and then eventually it's going to stop completely. And once again, the way I do these diagrams, a dot means stopped. The length of the arrow shows how fast the ball is moving. So here it's moving more quickly. Here not quite as quickly. It hits the spring, and then eventually it stops. So to start with, 1, 2, 3, 4, 5, 6. I decided we would start with 6 bars of energy. And at this point, since it's going slower, I said, okay, let's say it's only got 4 bars of energy left. So here's the first question. Where did the other 2 bars of energy go? Because this is a closed system. So if it's a closed system, the energy has to go somewhere. And the answer would be those 2 bars are thermal. As it just hits, we are assuming that there is no elastically stored energy in this spring yet. Right? It has to be after it hits it and starts pushing it in. So that was kind of one of the struggles that some of you had going through some problems like this the first time. So it looks like this. So the question is, what happens when the spring is pushed in? This stops, right? And the other thing that a bunch of you do is, oh, it stops. Everything has to be thermal. Well, the only time all energy becomes thermally stored when an object stops is if there is no other energy in anything in the system. And exactly, in the ball, there is no other energy. True. On the table, there is no other energy. True. But when the spring is pushed in, there is a form of energy that is stored in the spring. So, and it's not going to be thermal energy. When the spring gets pushed in, it is going to be elastic energy. So there is definitely some elastically stored energy now in this whole system. And it's actually in the object of the spring. The question is how much? Once again, I don't know. It could be 2, it could be 3. It's probably not going to be 4 because we already had 2 bars of thermal energy here. So we're probably going to have at least another bar here. So it would probably not be too far-fetched to say 3 and 3. So once again, the only time when an object stops that all of the energy is going to be thermally stored is if it's probably like at the bottom of the hill and stops. So there's no gravitationally stored energy. It's not interacting with anything like a spring. All right, and so just kind of let me slide up to this next problem, which is not what we're going to look at. But this is another example that even though it is stopped, not all of the energy at the end will be thermally stored. There is gravitationally stored energy at the end because this object is higher than where it started. So as it goes uphill, part of that energy has to be gravitationally stored. So that was another kind of misconception that when going through these. I think that's probably enough to kind of give you an example or enough examples to see what's going on with closed systems with energy bar charts. If not, there's going to be lots of practice. I'm going to set up some discussions and things over the next week or two. Feel free to be part of those discussions. I will be talking about what is going to be required for you to retake exams and quizzes and things in a separate video in the near future. Until then, thanks for watching.